Assalamualaikum and hi everyone. My name is Ashikin binti Abu Bakar from Universiti Malaysia Perlis, UNIMAP. Today, I would like to present my conference paper entitled Numerical Solution of Mixed Convection Flow over a Moving Vertical Plate in Nanofluid. First of all, let me introduce to you the main keywords in the study. The first one is boundary layer flow is a layer of fluid closest to the surface of a solid past which the fluid flows. The second one is mixed convection is a combination of natural and forced convection mechanisms to transfer heat where both pressure and buoyancy forces interact together. Number 3, heat transfer is the movement of heat energy from hot to cool region until both regions are in thermal equilibrium. Number 4, moving plate is a plate in which the fluid has the same velocity to it. Number 5 is nanofluid, a mixture of the base fluid and nanoparticle with diameter 1 to 100 nanometer size. This term is introduced by Choi 1995. And the last one, in the study, we are using nanofluid model that introduced by Theory and Das 2007, where it is considered the effects of nanoparticle volume fraction to the flow and heat transfer. This is the physical model of the study where we have moving plate, nanofluid boundary layer, velocity profile, temperature profile, and the yellow arrows correspond to VW where suction and injection occurs here. There are two problem statements in the study. The first one is how does the mathematical model for mixed convection is formulated. The second one, how does the effect of nanoparticle volume fraction to the flow and heat transfer characteristic. And we have objective to extend the problem of mixed convection boundary layer flow over a moving vertical plate to the case of nanofluid. And then the second objective, we continue to construct the mathematical formulation, design an algorithm, and interpret numerically the mixed convection boundary layer flow and heat transfer. And the scopes considers steady laminar incompressible flow, two-dimensional boundary layer flow, moving vertical plate theory, and thus nanofluid model. In this section, we carry out only the main literature review to present to all of you. The first one is Perro et al. 1959 introduced the study of mixed convection boundary layer flow, while Choi 1995 introduced the term of nanofluid, and Bakar et al. 2013 investigated the mixed convection boundary layer flow over moving vertical plate in the viscous fluid, and Theory and Das 2007 introduced the nanofluid model with the effect of nanoparticle volume fraction. And for the present study, we continue the work of Bakar et al. 2013 to the case of nanofluid. In research methodology, there are 4 steps to finish the paper. For the first one is problem formulation, where we need to formulate the mathematical model in partial differential equation, PDEs, and then proceed to mathematical analysis. We use the similarity variables to transform the PDEs into ordinary differential equation, ODEs, and then next we do programming to apply ODEs in shortcode program and guess the initial values. And the last one, for numerical solution, the numerical results are presented graphically and have been compared with the previous literature. The partial differential equations are given by 3 equations. For the first one, continuity equation, the second one, momentum equation, and the third one, energy equation, subject to boundary condition, equation 4. We use similarity transformation to transform the PDEs to get ordinary differential equation ODE subject to the new boundary condition. In results and discussion, the numerical output contains physical quantities that are velocity profile, temperature profile, skin friction coefficient, and local Nusselt number, together with the physical parameters nanovolume fraction, VARFI, mixed convection parameter lambda, velocity ratio parameter epsilon, and suction injection parameter S. Table 1 is the thermophysical properties of fluid and nanoparticle that introduced by Olstop and Abunada in 2008. In this paper, we use fluid-based water and nanoparticle copper, titania, and alumina. Table 2 shows the comparison between present results with Bachu et al. 2013, and from the numerical result, it shows that the result has good agreements. Figures 3 and 4 represent the variation of skin friction coefficient and local Nusselt number respectively with mixed convection parameter lambda for different nanoparticle volume fraction VARFI. For copper water base, we notice that the value of skin friction coefficient in figure 3 increases when lambda increases. Meanwhile, the opposite effects are observed in figure 4. However, the skin friction coefficient and heat transfer rate for VARFI 0.2 is lower than 0.1 and 0. It is because the presence of nanoparticle tends to reduce the skin friction coefficient and heat transfer rate. From these figures, the dual solution exists up to the different critical values lambda c, and there is no solutions beyond this critical value. The variation of skin friction coefficient and local Nusselt number with suction S for different nanoparticle copper, alumina, and titania are provided in figure 5 and 6 respectively. It is shown that the only dual solutions exist for the given suction and injection cases. After the point suction critical SC, we found that no solution exists. When S increases, the value of skin friction coefficient in figure 5 increases. And in figure 6, the value of local Nusselt number also increases. As we can see from these figures, nanoparticle copper has higher values of the skin friction coefficient and heat transfer rate. It is related to higher thermal conductivity of copper compared to alumina and titania. Next, figures 11 and 12 are velocity and temperature profiles for different mixed convection parameter lambda when VARFI equal to 0.1, S equal to 0.1, epsilon equal to negative 0.35, and Prandtl number equal to 6.2, respectively. It is worth mentioning that all the velocity and temperature profile presented in figure 11 and 12 satisfy the far-field boundary condition asymptotically and thus support the validity of the dual solution obtained. There are three main conclusions in the study. The first one is dual solution were found exist for both suction and injection S and the presence of nanoparticle volume fraction. The second is the presence of nanoparticles tends to enhance the skin friction coefficient and the heat transfer rate. And the last one is the skin friction coefficient and heat transfer rate for nanoparticle copper water based fluid is more dominant compared to the nanoparticles alumina and titania in water-based fluids due to the higher thermal conductivity. This is all the references that we use in the study. Continue. Lastly, this work was supported by Fundamental Research Grant Scheme (FRGS) from the Ministry of Higher Education Malaysia. We wish to express our thanks to the reviewers for their good comment and suggestion. That's all from me. Thank you.